and you're going to take chapter 2, quiz 1. This also happens to be a homework question. So you're going to get double the benefit. You're going to get the quiz correct, and this is going to basically pretty much be a repeat of a homework problem that the homework is due on Sunday. All right, so let's just start jumping into it. And I'll go off on tangents and deep dives and, talk a lot about other stuff related and maybe not related, but let's get started. An electron moving along the x-axis. So this is, we are starting off this course with the subject known as one-dimensional kinematics. One-dimensional. How do I know it's one-dimensional kinematics? Because it's basically saying it's moving along an x-axis. So there's X, Y, and Z. It could be 1, 2, or 3-dimensional kinematics. In this case, it's one-dimensional kinematics because of the specification. So let's draw an electron moving along an axis. Here's an x-axis. Here's an electron sitting on this x-axis right there. An electron is moving along this x-axis. This electron is being guided by a position function. So let's say this is an electron, E minus. So this is the typical designation for an electron. For example, this is a popular definition for a proton. This is a popular definition for a neutron. This is the symbol, not definition, but symbol. This is the symbol for electron. We're dealing with an electron, and this electron is made to move according to this function. So imagine you have an electron basically just constrained to move in one dimension, and on top of that, it's made to move very specifically with a very specific function like that. And then you ask yourself, how can you control an electron? Aren't electrons sort of like free agents or free spirits? I mean, how do you control an electron? And the answer is there's a lot of ways. You can control an electron. One way is through magnetic fields. So if you subject this electron to the right kind of magnetic fields, it can exhibit a very specific kind of motion. So this is going to go fast, but it's a good introductory question. If this electron is moving according to this function, how far is the electron from the origin when it momentarily stops? So let's do some explanation. So what I'm doing here is going to be very similar to what you're going to do during an exam. You're going to explain what you're doing very clearly. You're going to provide associated visuals like I'm doing, and you're going to get the right answer. So you might think, don't I really just need to cough up the right answer and who cares about the rest? Nope. You need to get the right answer, and you need to explain yourself thoroughly, as opposed to explain yourself superficially. Superficial explanations just don't cut it. Imagine that you're working for SpaceX and you hire me to modify a nozzle design for one of the SpaceX rocket engines, and I give you like the right analysis. I give you the right numbers, numerical data, but I don't explain how I came to this result, what kind of testing I use. You would no way take me serious. So let me try to make good on that commitment, because this is what you guys are going to do on the exam. Let's see, how far is the electron from the origin when it momentarily stops? So I'm just going to start doing what you'll be doing on the exam. When the electron momentarily stops, what's true? Its velocity equals 0. That's kind of a no-brainer. I mean, it's a no-brainer when you've seen these problems a few times. For those of you who have never done any type of, well, that really can't apply, but a lot of people, physics problems are basically like story problems. They're story problems like you're used to in math, but they pertain to the physical universe. So a lot of times it's just a matter of doing enough of these physics problems to sort of get into the mood, to get yourself sort of acclimated or pointing in the right direction as far as describing what's going on. When this electron comes to a stop, its velocity is equal to 0. And then again, pretending that this is actually an exam, because you're going to have to do what I'm doing on an exam. I know velocity, which in this case is a function of time, is defined, triple equal sign means defined as the derivative of the position function with respect to time. So you should know that. Well, not necessarily. You may or may not know that, but typically speaking, you guys, you will absolutely know that before any of our lectures, because you have access to the lecture videos. And on Thursday, I'm going to give you the green sheets. So let me show you what these green sheets look like here. This is basically what you see on the lecture video. The lecture video is me filling in these blanks. And as I'm filling in the blanks, I'm talking through, key points and providing reinforcement. So going forward, this is not true this week, but starting in week 2 of our class, whatever you do, don't come to a lecture without having digested the lecture video and completing the green sheets. I mean, you can if you want, but it's a bad practice. It's so much better to get your head screwed on straight before you come to a lecture instead of seeing things for the first time in a lecture. And what I'll do is, starting with week 2 or in week 1, I'm going to assume that you've digested, at least gave yourself a first exposure to the lecture video and the green sheets. So that's why I'm going to say, well, you know that the definition of velocity is dx dt, and you see that down here. So everything is going to be spelled out. Instantaneous velocity. Yeah, right here. All right. So everything's going to be spelled out in these green sheets. And on top of that, you get to use these green sheets during an exam. So you have a real incentive to filling out these green sheets and watching the lecture video, because you get to use the green sheets, the actual physical paper green sheets yourselves on the exam. And this is how you learn. This is the background information that you need. So in a normal subsequent to today, I would say, well, you guys know from the green sheets in the lecture video that the definition of instantaneous velocity is dx dt. So for now, though, I know you might not have had that digestion. So this is why I'm going to be maybe a little bit extra explanatory, but this is what you would do on an exam anyway. So I know velocity is dx dt. So I guess all I'm going to do now, not all, but my next step will be, I'll string it here, equals, what is the time derivative? What is the time derivative of my x function, of my position function? Here's here's my position function, 17t e to the minus t. So that's provided to you. Again, how do you make an electron behave this way? Magnets would be one idea. Some sophisticated magnets and timing devices and tubes and stuff like that. So again, this is my position function. So all I need to do is take the derivative of that, set it equal to 0, and then see what I'm going to do there. So I know how to do derivatives. You guys have to be very proficient with derivatives and integrals. If you haven't taken Calc 1, you shouldn't be in this class. And I think everyone has taken Calc 1, but for sure, we're going to do calculus. And oddly enough, there's not a tremendous amount of calculus in the class. A lot of the calculus we encounter is in chapter 2. So it's kind of front loaded a little bit as far as the calculus. The calculus isn't that deep, but you do have to know, again, how to take derivatives and do integrals. And to try to take this class without having first taken Calc 1 makes no sense. You should think of a different field because you're not aiming yourself in a good direction as far as science or computers or engineering is concerned. You're literally hurting yourself by going out of order. All right. So, but again, I don't think that applies to anyone here. So I'm going to take the derivative of this function. So this is product rule. So product rule says if I take the first derivative of this position function, it's going to be first times the derivative of the second plus second times the derivative of the first. That's the derivative. And just know that, again, little sidebar, dx dt, basically, what is this doing? This is telling you the rate of change in object's position. This is what derivatives do. Derivatives are basically slopes. When you do a derivative, you're basically taking a slope, which is a rate of change. And specifically, I should include it's the time rate of change. There's a lot of rates. You could have a positional rate of change or temperature rate of change, but we're talking about the time rate of change in an object's position, not positive. Let me fix that, position. This is why you learn, among other reasons, this is one of the reasons why you learn how to do derivatives, because they give you the rate of change. And it just so happens that the rate of change of an object's position is known as velocity. And you've seen velocities. You're driving down 275 and your velocity is well, if it's 275, if you're driving down 275, your velocity might be 55 miles per hour. So that's a rate. It's the rate of your change in position. It's the rate of change of your position. Every hour, my position changes by 55 miles. So this is why we're leaning on derivatives. The one other thing you should mention, it's the instantaneous. I'll just keep tagging along. You guys should be taking notes. That's the other thing, guys, just the best practice. If you ever find yourself just sitting back and watching like this, you know you're doing the wrong thing. You should constantly be taking notes or doing something. Just get out of that. Don't ever let yourself do what I'm doing. That's just, that's not something you typically see at this level and above. You don't often see pre-engineering students or pre-computer people like sitting doing nothing. So this is the instantaneous time rate of change of an object's position. All right, so here's my velocity function. So let me simplify. If I simplify this, I have my velocity, and then this parenthesis, t parenthesis means that's assessed velocity, and that t enclosed by parentheses is just means it's a function of time. Velocity is a function of time. And if I simplify this, what are some common factors? 17e minus t. All right, so if I pull out 17 is common to both of those terms. E minus t is common to both of those terms. So with pulling out those common terms, 17e, I can see this would be 1 minus t. Pretty anticlimactic, but pretty simple. That's it. This is my velocity function. Okay. That's my velocity function. So now all I have to do is, again, set velocity to 0 and then find the time when this happens. Find t at this moment. So really statement number 4 is sort of the game plan. And then use this t to find the position, because that's what we're after, to find x. Okay, that's the game plan. We're almost there. Number 5. This is, let's see. So velocity at some time equals 0 when, well, let's see. Can this term ever be equal to 0? No. This term can never be equal to 0. This is natural log base e raised to some power. Natural log base e raised to any power can never be 0. But this term can be 0. So velocity equals 0 at t equals 1 second. Okay. So number 6 says, well, okay, plug into x function, plug into my position function, plug into position function. and then we're going to be done. So if I plug this into my position function number 6, I have my position function at 1 second. That's why I'm doing parenthesis 1 parenthesis equals E. No, what is it? Equals my position function equals 17 times T times E to the minus T and this one. So I'm basically recycling this. This is my position function. Let me just make that clear because again, this is my position function is X is a function of time equals 17 T E to the minus T. Okay, that's good. And then I guess it's time to do calculator. So calculator says 17 times, and you might have different numbers. I have 17. Maybe you have some number that's not 17. It doesn't matter. You use your numbers. 17 times E to the minus 1 is 6.25 and some change. So I'm getting 6.25395 and on and on and on. So it's basically 6.2935 and some change meters. We have to always worry about meters, which is the right number. And if you notice, Wiley Plus is basically just showing 6.25. Wiley Plus basically says you have to be within plus or minus 2% of the precise answer, not the rounded answer, but the precise answer. So in terms of sig figs, I mean, basically the approach I use in this class is keep all your precision of precise answer. So my precise answer, according to my calculator, is 6.259505. And as long and that puts me within 2%. So 6.25 certainly puts me within 2% of the 6.2539505 answer. So that's it. This is our first problem. So at this point, you guys, you should be done or on your way to being done with this problem. And you should be thinking of questions to ask if you have any questions. If you have questions for me, unmute your mic and ask them. Otherwise, if you just want to throw something in the chat box, do that. And you guys can chat away amongst yourselves via the chat box. But let me just take a little temperature here. I can see how everyone's doing. No one gets left behind. So if I go to grades, nope. So that's our first quiz problem. Not only is that a quiz problem that you got completely correct, but that's actually the same as the homework problem that you're going to have to finish by Sunday. But when you do the homework, maybe think on it a little bit harder. And we're actually not done. We're not going to move on past this one yet because we have to do a little other sort of associated activity. Okay, so is everyone done? Chapter 2, quiz 1. Quite a few people are done. Not everyone's done, but yeah, most people are done. All right, so now let's do something new. This is another, I'm going to count this next thing you're going to do that's associated with this as another quiz. And these are all 1-point quizzes. Overall quizzes comprise 5% of your grade. So they're not meaningless, but again, the purpose of a quiz is to get you ready for the exam. So that's why you can't stop worrying about a quiz question just because you get it correct. You can only be okay. You can only be content when you get the correct answer and you have the deep understanding. Go ahead, open a browser, open a web browser.
Could I ask a quick question?
Yep.
On the problem you were doing?
Did you have a question?
Oh yeah, sorry. I was looking at it where you pulled it up, but I can go back to my notes. You see where you simplified it to the 17 E minus T and then 1 minus T.
Right.
And then you were talking about it. I was trying to you said that since it was a log function, it couldn't go to 0. So you chose to use the 1 minus T, right?
No, I didn't choose to zero. I had no choice. I mean, when does when does this expression equal 0? Is there this term right here? This term can never equal 0. So your only option is, since this term can never equal 0, you have to look at this term. Can this term ever equal 0? Yeah, it can. This can equal 0 at t equals 1 second. So that's the thought process. This term right here, never going to equal 0. So how do I have a 0 velocity if this term is never going to equal 0? And the answer is, well, look at this term. Does that make sense?
Yeah, that makes sense. Okay, thank
All
you.
right, good. Good. So now, because again, we're not quite done. Open up a browser, get yourself to Desmos. Right here, Desmos. Not Demos, not Demos. Desmos. Desmos. Let me make sure you're seeing what I'm seeing. Desmos. D-E-S-M-O-S. Desmos. So Desmos, beautiful free math. Let's graph this. Graphing is very helpful, you guys. I'm gonna try to nudge you to graph stuff as often as I can, because that's kind of a very sort of hidden secret. Like, the better you are at graphing stuff and interpreting graphs, the stronger you're going to be, not only for your future classes, but your future career endeavors. So everyone's now up and running with Desmos. And then let's go ahead and graph your function. So let's all use your function. I'm going to use my function. You're going to use your function. So for me, here's my position function. If I remember, my position function is 17t e to the minus t. So I'm gonna plot that. I want to see what that looks like graphically. 17t e to the minus t. So ready? Just do y equals 17t times e to the up caret minus t. So instead of typing t represents the independent variable. For this graphing application, the independent variable is taken as x. So instead of 17t e to the minus t, I'm just using 17x e to the minus x. That's my position function. Okay, so right below that, let's go ahead and plot the velocity function. Y equals, and then just refer back to your notes. My velocity function was right here. I buried it with stuff. So my velocity function is 17t. This is my velocity function. Okay. So I'm going to go ahead and just graph that. That's my velocity function, 17e minus t. Y equals 17t times e to the minus t, all of that times t minus 1, was it all of that 1 minus t. 1 minus t. There it is. 17t e to the minus t. Hang on, I got to fix that. It's 17, not 17t. Okay, there it is. 17 e to the minus t. 17 e to the minus t times 1 minus t. Okay, that's it. So you're looking at this red plot is position. This blue plot is velocity. And you can adjust this screen. So watch what I do. I'm going to put my mouse cursor right on that horizontal axis, the y equals 0 axis. Hold down the shift key and then just drag it so I can scale it like that, or I can hover my mouse right on the vertical axis and I can hold down the shift key and I can scale it like that. So I can pan and zoom so I can adjust. But this is a great graphical overview of how this electron is behaving. This red plot is the electron's position as a function of time. It's just moving in one direction. So don't look at this and think, oh, it's moving in two directions. This is one-dimensional motion. Here's the electron's velocity as a function of time, and here they are together. So now, if you remember, we basically said, when does this velocity equal zero? Because that's when it momentarily stops. So you can see right here, this blue plot, this is my velocity function right here. And sure enough, if you trace this curve all the way down to when it equals zero, right there, look at that. This is basically saying at time equals 1 second, my velocity is zero, which that agrees with the math and physics that we just went through. So that's good confirmation. And then the question also asked, well, at this particular point, where is my electron at the moment it stops? So turn on your position function, and then I can just trace right there. At 1 second, notice I'm clicking on my position function. At 1 second, my electron is 6.254 meters away. And again, also at 1 second, its velocity is zero. And you can see the slope of this point right here where I'm pointing, the slope of that tangent line equals zero. So that's a calculus thing. We'll get into that. But right now, this is what you need to submit. So go ahead. I'm going to put something in Blackboard, and you're going to submit a screenshot of this into Blackboard. So let me log into Blackboard and make a little submission area for this. So I'm logging, and I'll show you everything I'm doing here. I'm logging into Blackboard. Here's our class 211, 145, 113. We can go into course documents, and I'll just make a little repository right here. This will be an assignment, and I will give this the poetic name as Chapter 2, Desmos. Exercise number 1. Chapter 2, Desmos, exercise number 1. That's in Blackboard. Is that good? That's good. Deadline, let's see. It's now 1:35. I'll just, maybe make it due at 2 p.m. So I'll display this until 2 p.m. Not like that, I won't. So today is Tuesday, August 31st, and this can be due at 2 p.m. in case you need to work out some kinks. I know all of this is new. Don't panic. I know I'm throwing a lot on you, but your job is just to ask questions or request, for me to repeat something or extend something. But you should always be in the middle of doing something. All right, so that is good. Points possible. Everything will be a 1 point. Everything except for a few exceptions is worth a point. So these are all quiz activities are worth 1 point. So due date again is today at 2 p.m. Now what you're going to do. So now this is available in Blackboard. Chapter 2, Desmos exercise number 1 is now available. So all you need to do is to get into that and then submit a screenshot. So what I would do, once you have Desmos all perfected, and your Desmos should look like this, at this point, except you're not going to use 17. I think we all have different numbers. You're going to use your number. Oh, and one other thing you should do here, a note. Open up a note and type in your name. So my first name is Chris. My last name is Wood. There. All right, and again, let me know. Unmute your mic and ask me some questions if anything is less than clear. But you should have the following items on this screen. You should have your name. You should have the position function with your numbers, not my numbers. You should have your velocity function. Oops, except I just deleted it. So y, there it is. Okay, and then your 2 plots. So that's it. Name, position function, velocity function. When you get all of that done, go ahead and take a screenshot of it. Save it, save this. Actually, I would probably use snip take a screenshot of this, save it to a file. So the way I typically do it, you can do it a lot of ways, but snip or just screenshot it to a file. But this is all I need. I don't need every piece of this screen. I just need the graphical part and those 3 items. Again, name, position function, velocity function. I'm going to save this to a file, save as, and this is chapter 2, Desmos exercise 1. There it is. So then when I go to Blackboard, you're good to go. So when you get your Desmos graph all tweaked out, name, position function, velocity function, showing the graphs nice and sized, so they're very easy to see. Go to Blackboard, and then when you're in Blackboard, go into course documents, click on Desmos exercise number 1, and go ahead, attach, browse local files, and my local file is not there. Desmos documents. Let me find out where Desmos put it. All right, so I'm going to do that. Let me do this again. Snip function or whatever function you feel like using. Snip function, new. This is it. This is the sweet part of the graph. Name, position function, velocity function. I'm going to save as, oh yeah, and it was going to the wrong area. I'm going to save it. Chapter 2, Desmos exercise 1. So there. Anyway, so now that you're in Blackboard, so now that I figured out where I put that, again, get to Blackboard and then do browse local files. And there it is, Desmos chapter 2 exercise number 1. And then you can see it's attached. It's attached right here. And then hit submit. And you're going to be done. Position from previous, that's fine. So just, you are officially, so you've just completed 2 things. You've just completed chapter 2 quiz 1, and you've just completed chapter 2 Desmos exercise 1. So you have all of that now behind you. Let me just take a look at the grade center to make sure everyone's submitting this.
Professor, I don't know if it was just like a coincidence or not, but I actually did have the same numbers as you.
Yeah, that's fine.
Okay.
That's fine. Yeah, I bet a lot of people did. So maybe even everyone, I don't know. But just make sure though, when you submit, you're including your name, so this is going to be your name, not my name right here. And then your position function and your velocity function. And if you have the same numbers as me, that's fine.
Professor, I don't see a place to submit this.
Log into Blackboard. When you log into Blackboard, you're going to click on course documents, and under course when you do that, you're going to see chapter 2 Desmos exercise 1.
Got it. Thank you.
And then you're going to browse your local files and select that screenshot you just saved, however you want to save that, and submit it. Okay, that's good. And then when you're done.
I accidentally sent a screenshot without the my name in the equations.
Okay, is that you, Lewis?
Yeah.
All right, so Lewis, I'm going to go into your submission right now, and I'm going to clear your submission.
Could you clear mine too? I did the same thing.
Okay. So first off is Lewis Stark. And clear. So Lewis, you are cleared. And then who else was needing the same thing? Was that Jacob?
Yeah.
Jake, what's your last name?
Edwards.
Jacob Edwards. Last name Edwards. Oh, okay. Jacob Edwards. Clear attempt.
Professor, could you remove mine as well? It's under Will.
Yeah, you guys. Okay. I mean, not to sound snarky, but instructions are important. So Will. Clear attempt. All right. Good. So again, let me just repeat at this point. Let me go into Wiley Plus. So the title of this next 2-minute conversation is How to Cheat in Physics. So let me go Wiley Plus. And let me go into our assignments. And we just did the chapter 2 quiz. For section 145, 113. All right. Chapter 2, quiz 1. All right. So here's one way you can cheat. There's lots of ways you can cheat. Let me show you one way, which I think is the easiest way to cheat. In my humble opinion. Oops, previous. Okay. So all you need to do, one good way to cheat is just literally take a portion of the problem statement. So here's chapter 2. Here's our quiz question. So we can kind of completely bypass the learning process and cheat by doing the following. Just take a portion of the question statement, copy that, and then go into a Google window, a Google input window. So, and then paste that portion of a problem statement in Google. And then there you go. So right here, if I just copy and paste a portion of the question statement into Google, there's 13 ways to get a solution to this problem. Here's one from Chegg. There's another one from Chegg. But maybe you don't feel like subscribing to Chegg, so you just go to Quizlet, or maybe you look at this YouTube video from Kevin Academy or WNY Tutor. I've heard students using that before, or Topper, or so on and so forth. So now here's the thing. And if you didn't know about this, well, I guess shame on me for corrupting you, but I'm kind of assuming most of you know that you can look up the solutions to all of these problems. Here's what I would suggest, though. I'm not saying don't do that. Shame on you. I'm saying what you should really do if you're interested in really learning this stuff and doing well on the exams and being a better computer person or science person or engineer. Deep learning. This doesn't lend itself to deep learning. So here's what lends itself to deep learning. All of this stuff right here. All of this stuff that I'm talking through using a lot of time. And then the other sort, here's a better way to cheat as well. If we go back to our class page and make sure you hot link, you bookmark this link. If you go to our class web page and you just click on deep dives. If I click on deep dives and chapter 2, so I'm in the chapter 2 deep dives. This is just like all of those other cheating sites, which again, Topper, Chegg, Course Hero, Slater, WNY, so on and so forth. But now here's the one thing I believe is different. These deep dives go into far greater detail. So if you're going to look up answers, which you should do, and I'm giving you the answer now, I'm just saying, make me your first option. This is not an ego thing. This is just a tactic that I'm trying to push on you to help you deeply learn this stuff and do well on the exam. So here's one of my deep dives. There's problem 17, which we're getting to pretty soon. And look at all that. Look at all this explanation. So this goes into far greater detail. And you might think, here's what you absolutely could think. You could say, geez, it's going to take me 10 minutes just to kind of step through this, maybe 20 minutes. Whereas if I just look up the answer in Chegg or Coursera, if I just Google the answer, I can be done in 5 minutes. And obviously, you're going to pay a price, or you're very likely going to pay a price. Finishing in 5 minutes is probably going to result in a lot less deep learning, residual learning than going through and fighting the good fight. It's the John F. Kennedy quote. Why did we choose to go to the moon? We choose to go to the moon, not because it's easy, but because it's hard. So in this case, I'm thinking of John F. Kennedy. Why should you use this approach? You're not going to use this approach because it's easier, saves time. This is the hard way to do things, and it's the better way. So, and it's not going to be crazy. It's not going to be a crazy amount of additional time. So there's a lot of talk about that subject. I'm going to get ready for quiz 2. And again, just to keep reinforcing, if you guys want to chat amongst yourself, use the chat box. If you want to unmute your mic and ask me something, that's you should do that as well. So we have just done 2 assessments. And what that quiz you just did is is exactly like your homework problem. All right, so quiz 2, what is that? Let me get quiz 2 ready. Okay, quiz 2 is 2:15. Let me check on something. Gotta look for something. Okay, our next quiz will be homework problem number 15. If a particle's 4 minus 12, 3t squared. Okay, so let me fix this. Give me another minute. I got to do some editing here. This is chapter 2, quiz 2. The title of chapter 2 is Motion Along a Straight Line, which is one-dimensional kinematics. Okay. So this quiz problem will be, again, identical to a homework problem. So you're going to see this at least twice. And I think I'm about ready for it. This is a quiz. It's now 1:51. We'll take a break pretty soon. But right now, I'll open it up. 2:30 p.m. and we are good to go. I think. All right. At this point, you should see chapter 2, quiz 2 in Wiley Plus. Let me know if you can't, and I'll have to fix something. But chapter 2, quiz 2 is now what we're doing in Wiley Plus. So let's get started and do some more math and physics. Okay. All right. And again, this is just like the homework problem. And then you might think, how great is this? This instructor is doing all of my homework and all of my quizzes, but it's not quite that beneficial because you need to learn from the quiz experience and from the homework experience. And then you need to do a whole lot more practice. I'm going to give you a practice pool where you can practice just to make sure you're ready for the exam. Because the exams will be consistent with the homework problems and the quiz problems, but they're going to be mixed up a little bit. So they're not going to be identical. They're going to be in the same family, but not a copy and paste. Here's our next quiz. This is quiz 2. Another particle is undergoing sort of program motion. So you as a computer engineer or a programmer, I used to do this a lot. I used to program stuff to make stuff behave a certain way in the physical universe. So I remember I used to talk to students who were going into, and I think there's quite a few of you who are going into computer engineering or computer science, thinking that, again, maybe you're going to have something to do with software engineering, programming, software architecture, so on and so forth. And in many ways, I've learned this. In many ways, physics is arguably more important to you than it is for like a mechanical engineer or an aerospace, or I should say just as much. So for those of you who are going down a computer path, you need to have a good, or you will benefit from having a good understanding of physics, because you're very likely going to have to interface with the physical world. Like, for example, what interfaces, what kind of technology that you program interfaces with the physical world? Robotics, mechatronics in general, mechatronics, driverless vehicles. I mean, the list goes on and on. Driverless vehicles, drones, on and on. The list is endless. There's something called IoT, the Internet of Things, which means everything, at some point, everything in existence is going to be inundated with sensors. And those sensors collect data, and that data is basically processed via algorithms. And that's where you come in as a computer science person, or a computer engineer, or a programmer, software engineer. So anyway, let's do this problem. We have one-dimensional motion. Why? Because again, this is just constrained to the x-axis. So let's start going through this. Number one, well, you always need a picture. So here comes the picture that's always needed. In fact, I don't need, yeah, that's fine, I suppose. Here's my particle. My particle is moving. This particle has you as a computer person, or a robotics person, or a mechatronics person. You have developed the software that makes this particle move according to this function. Mine says 1 minus 12t plus 3t squared. And think of cruise control. Think of the Mars Perseverance lander that's roaming around on Mars. There's just a ton of things that are moving according to some programmed algorithm, which is basically just having this function exist in software. Okay, so question number one, what is the velocity at 1 second? Well, so far this seems pretty easy. So once again, velocity, which is a function of time, is defined as the time rate of change of position. We've done this before. So all you have to do is to take the time derivative of this function. For me, it's 1 minus 12t plus 3t squared. And I know how to do the power rule in calculus. So this is going to be minus 12 plus 6t. And once again, this is my velocity function. So pretty straightforward. This is a pretty low degree of difficulty problem, but everything's hard at first. Every problem is hard when you first see it, and this is no exception. Okay. So it says, what is the velocity at 1 second? The velocity at 1 second is number 2. So velocity at 1 second equals minus 12 plus 6 times 1 second. And the units here, collectively, the units are going to be meters per second. And you might say, how do you know that's meters per second? And that's a good question, because right here, and this is actually non-trivial, in which x is in meters and t is in seconds. So this t is in seconds, that's in seconds. So this would be seconds squared, that would be seconds, and x is in meters. So when I take the derivative, remember what a derivative is. Derivative is basically a slope or a rate of change. So if dx is in my numerator, so the units for dx would be meters, because that's basically tracking, that's addressing the object's position. So in terms of units, this would be meters in the numerator. The denominator would be seconds. So you do, and I'm going to start stressing dimensions a lot, but for now we're good to go, because you can see that minus 12 plus 6, using my numbers, not yours, equals minus 6 meters per second. This is the answer to part A. Pretty plug and play. Not a whole lot of not a whole lot of hard thinking is needed for this. We're done with part A. Part B says, is it moving in the positive or negative direction? So let's do this. Back to Desmos. Go ahead and plot your function in Desmos. Everyone to Desmos. So this is time well spent. You're going to benefit, whether you know it or not. You're going to benefit from being able to graph stuff, no matter where your future brings you. So I'm going to graph my position function. My position function is 1 minus 12 plus 3. 1 minus 12 plus 3. So 1 minus 12 plus 3x squared. That's my position function. And let me just double check that by going back here. 1 minus 12t plus 3t squared. And again, I'm replacing the t's with x's. X is my independent variable. And now here's the velocity. Ready? Y equals minus 12 plus 6x. I think I can actually change this. Can I? I think I can call this x. No, I can't. Can I? No, I can't. I can't. All right, so that's fine. That's fine. And then maybe I'll adjust. So hold down the shift key and with your mouse on the y equals 0 axis or x equals 0 axis, you can go ahead and adjust your view so things are fitting nicely. Ooh, that's a very good picture, right? Look at that. Perfect. So that's what your Desmos is looking. This is how my object is moving. I just said at 1 second, I know the velocity. Let's just do a sanity check there. So at 1 second, here's 1 second. At 1 second, there it is. At 1 second, according to my graph, my velocity is -6. So that makes sense. So now part B is saying, what's the direction of this object at this moment in time? Is it moving in the positive or negative direction of X just then? Well, if I look at my graph, my Desmos graph, I can see that at t equals 1 second right here. That's not 1 second. At 1 second right here, my velocity is negative. Okay. So not only do I have a negative velocity means I'm moving away from the origin. So that's the interpretation I can make. At t equals 1 second, I have a negative velocity, which means at t equals 1 second, basically at t equals 1 second, my object might be here. So let me put my object at some location at t equals 1 second. So at t equals 1 second, is it moving in the positive or negative? This is the direction of my velocity right here. I should draw that. Ready, set, go. There it is. This is velocity at 1 second equals -6 meters per second. So that's what that minus sign is telling you, saying, hey, your magnitude is 6, but your direction is in the negative X direction. Okay. So that's the answer to B. So we're done with part A, done with part B. Part C says, what's the speed? Here's some physics trivia. Here's some kinematics trivia. Actually, for number 3, for part B, I should say, since V equals -6 meters per second at t equals 1 second, particle is moving in the moves in minus x direction. And I showed that. I gave a good visual of that. So here's a visual showing that. And then I just gave a little comment here too. Number 4 for part C, saying, what's the speed? And here's again some kinematics trivia. Speed. We've all used those terms. What's the difference between speed and velocity? velocity is a vector. It has a direction and a magnitude. So let's just say speed, let's just call it little s for speed, is basically the magnitude of the velocity, or just the absolute value of it. The absolute value of it or magnitude, it kind of means the same thing. So the question is, what is the absolute value of -6 meters per second? And that answer is not -6 meters per second, but +6 meters per second. So that's the answer to C. So we have 3 down. This is the answer to C. This is the answer to B. And D says, what is the speed? Is the speed increasing or decreasing? So you know what I'll do. This is a job for your Desmos graph. Go to your Desmos graph. And I think what I'll do, I'm just going to take a snip of this and put it right in my solution. And if this were an exam, you might be hand sketching this solution. So you would plot it on your calculator and then hand sketch the solution. And all of that will be very easy to do by the time exam 1 rolls around. So, but for now, I'm just going to copy and paste. Here's my Desmos screen right here. So it's saying D says what's happening at time equals 1 second. So here is, once again, time equals 1 second. Time equals 1 second is right there, that purple dot. All right, at time equals 1 second. So as time ticks away, as time flows by, I'm going to go from -6 meters per second to, like, say, maybe -5, -3, -2, so on and so forth. So you know what? Right here, right at the moment, time equals 1 second. The next moment of time actually has me going from, say, for example, -6 meters per second to -5.5 meters per second. Again, I'm just making up numbers, but for one thing, one thing for certain, speed is decreasing. Speed is decreasing because speed is just the magnitude of velocity without caring about the direction.
Are you writing stuff down?
Oh, yeah.
Keep going.
Yeah. Feel free, you guys. If I seem to be writing something down and you're not seeing, it might help to speak up right away. So that's the answer to D. Yeah, don't be shy, because wouldn't it be funny if I'm just ranting for an hour and no one says anything? That would be quite the hoot.
Wait, it looks like your speed is increasing though. I don't see why I'm not getting that, because your dots are moving closer to 0, so they're getting bigger. Those values are getting bigger.
They're getting smaller if you remember that speed is the absolute value of velocity. So at t equals 1 second, speed is equal to the absolute value of -6 meters per second,
Right.
which equals 6 meters per second. At t equals, just making up a number, at t equals 1.5 seconds, speed equals the absolute value at 1.5 seconds. It looks like I'm maybe about here, -2.5 meters per second. The absolute value of -2.5 meters per second is 2.5 meters per second. So that's why I'm saying, as I go from this value at t equals 1 to any value beyond, like the next moment of time, whatever is happening in the next moment of time, I know my speed is decreasing. I'm slowing down.
And your velocity is increasing?
No, the magnitude of my velocity is decreasing, and the direction is still moving the same. So that's the difference. And again, this is where those green sheet lecture videos are going to come in to play. But V stands for velocity. This is a vector. So you have to worry about 2 things with a vector. You have to worry about magnitude and direction. So what's the difference between velocity and speed? Velocity has a magnitude and a direction, whereas speed just has a magnitude. So if you talk about velocity, you could say, for example, you could say drive 55 miles per hour north. And if you talk about speed, the only thing you say, hey, just drive 55 miles per hour. If you're specifying a speed, you don't say 55 miles per hour north, because speed is a scalar quantity. Speed just is a magnitude, whereas v for velocity is a vector. Okay, so that's the difference between speed and velocity. In this case, as time flows to anything greater than 1 second, my velocity is getting smaller, my speed is getting smaller. And not only is my velocity getting smaller, but it is pointing away from the origin, like you see here. So as time ticks by, this arrow continues to point leftward, but it's starting to shrink. And at some point, you're going to stop. In fact, you're going to stop right here at 2 seconds. So those are good questions. These are like the finer points, but we have to be clear on some amount of terminology like this. Part E says, actually, let's see, C, D. Let me shrink this. We should say something about what we just chatted about. Okay. So for part D, it's saying part D, I'd say number 5, part D, at t equals 1, speed, I'll say speed drops from 6 meters per second to less than 6 meters per second. And then I'll say refer to graph, refer to my graph. And that's pretty sufficient for part D. Okay, so we're done with D. Part E says, is there ever an instance when the velocity equals 0? Well, here's the graphical way of answering that without even thinking. The answer is yes. There is a moment in time when velocity equals 0. And I can say that instantly because I'm just looking at this graph. My velocity equals 0 at this purple dot right here at 2 seconds. So my graph says velocity equals 0 at 2 seconds, but you have to do the math and physics part. You can't just say according to my graph, or maybe you could say according to my graph, but then I would also require you to justify using math and physics. And I'd say, since my velocity function is equal to minus 12 plus 6t, that's right here, I can see v equals 0 at 12 equals 6t, or t equals 2 seconds. So done with that. That's the answer to part E. Pretty good, pretty short and sweet. T equals 2 seconds is when the velocity equals 0. That was part D. Part E, sorry. The last part F. Is there any time after t equals 3 seconds when the particle is moving in the negative x direction? Well, let's see. Here's t equals 3 seconds. Let me just draw a line showing t equals 3 seconds. T equals 3 seconds is right here, right about there. All right, so that black vertical line is t equals 3 seconds. The question is, does the particle ever move in the negative x direction? And the answer is no, because, I mean, check out the graph. According to this graph, all times subsequent to t equals 3 seconds is showing a positive velocity. Positive velocity means moving away from the origin. So how can we say that in exam ready format? So this is part F. Part F says, I'll say the same thing, since V equals minus 12 plus 6t. And referring to graph, the answer is no. Refer to graph. No. Particle never moves in the negative direction. No motion ever again in minus x direction. And that's pretty good. So not only am I'm explaining it, I'm showing a function, I have a visual. So that's pretty sufficient. That's it. Those are 2 quizzes done. So this is part F. The answer to part F is no, which means you punch in a 0. 0 means no. All right. So it's now 2:15. Let's go to chapter 2, quiz 3. Let me double check that it's available. Our 3rd quiz and 4th assessment of today, chapter 2, quiz 3. Okay. Yeah, it looks good. All right. So let's do this problem because there's more new stuff to bite off. Okay. So I guess we're good. Chapter 2, quiz 3. This is also one of your homework problems. So let me just keep stressing that. It's 2 for the price of 1. The only reason I keep bringing that up is, take advantage of the fact that your quiz problems are the same as your homework problems. There's a right way and a wrong way to think of that. The wrong way is to think, oh, well, this will be a blow up. Homework will be a no-brainer, but that's the wrong way. The right way is to say, oh, maybe when I do the homework, that's when I can really make sure I understand the solution to this particular problem. So we have a salamander of the genus Hydromantes capturing prey by launching its tongue as a projectile. So here's a picture of Hydromantes. So there's a picture of a salamander launching its tongue like a projectile to catch a bug or a fly. So pretty impressive if you ask me. So we've done, the salamander's tongue has been studied. The kinematics of this salamander tongue has been studied. And here's what we found. This is a graph of acceleration versus time. So we know how this salamander tongue behaves as a function of time. As far as the acceleration, this is the first time we're talking about acceleration because kinematics is basically this: position, velocity, acceleration, and time. So we've talked a lot about position and velocity and time, but now we're going to talk about acceleration. So now here's the question. What is the outward speed of the tongue at the end of the acceleration phase? This is the end of the acceleration phase. The acceleration phase ends here. So this is the end of the acceleration. This is the start of the acceleration. And your job is to figure out what's going on. What is the velocity? What is the speed of the tongue at the end of this acceleration phase? So now what I'm going to do, just because you guys are thinking of potentially getting a job in the computer or engineering or science industry. So we all kind of think along those lines. I'm going to call this segment A. Seems to be an engineering thing to do. Break things down into components. Segment B, segment C, and segment D. And I know this salamander tongue is undergoing changes in velocity from segment A to B to C to D. So I guess this is my going in strategy. I'm thinking of number one, the velocity, and I'm kind of using velocity interchangeably with speed. The velocity of this tongue at the end of the acceleration phase is going to be whatever the change in velocity is during segment A plus whatever the change in velocity is during segment B plus whatever the change in velocity is during segment D. And last but not least, plus whatever the change in velocity is during segment D. So add up all of those changes. So for example, just hypothetical example, let's just say, well, from here, my velocity increased by 2 meters per second, and here it increased by 3 meters per second, and here it increased by 4 meters per second, and here it decreased by 5 meters per second. You would just add up all of those changes and get the net result. So let's go ahead. Now that we've broken things up into phases, I'm going to do this. How do I connect? So velocity, how do I connect velocity and acceleration? So I know I can say, because I've watched the green sheet lecture video, and you will have too. I mean, you're coming in, you normally would have watched the lecture video and finished the green sheets. I know that acceleration is defined as dv dt. So that's the definition of acceleration, instantaneous acceleration. So I'm just going to multiply through by dt. If I multiply both sides by dt, I get this. dv equals a dt. That's my relationship between velocity and acceleration, at least in this form. And I'm doing this for a reason. I'm writing it like this because I want to take the integral of the left side. So if I'm going to take the integral of the left side, take the integral of the right side. Whatever I do to the left side, I have to do to the right side. I'm going to give myself a boundary condition from some initial velocity to some final velocity. So now I'm going to solve the integral and evaluate it. So I'm going to get, well, I know the integral of dv is v. And when I evaluate it, I'm going to get v final minus v initial equals, and I'm not going to solve this there. I'm just going to leave this integral as an integral dt. And you know what? I can say here as well, vi, the initial velocity of the salamander, tongue is 0 because we're going to assume it starts from rest. And you might say, hey, Chris, it doesn't say it's starting from rest, but I'm saying, well, you know what? Because it doesn't specify the salamander's tongue velocity at t equals 0. It can be implied. I am stating, because I think it can be implied, that it starts from rest. So you know what? And this is a very commonly used expression. V final. And instead of V final is basically saying, what is your velocity at a point in time? And typically we just use that V. So I'm going to drop the subscript, because whenever you just see V without a subscript, that means the velocity at a given point in time equals, in this case, the integral of a dt. And in fact, I'm going to back up and I'm going to reverse myself a little bit here, because what if this initial velocity was not equal to 0? So I'm not going to cross that out. I mean, I think it does equal to 0 here, but I want to just handle the general case. So if that initial velocity is not equal to 0, then I would just there. Okay. So this is a very widely used, very often used expression. And you know what I like about this? I like the fact that I have this integral right here, because I know from calculus, the integral of a dt, let me try that again. I know this, this equals the area under an acceleration versus time graph. You should know this from your calculus class. This is pretty fundamental. In fact, this is technically referred to as the fundamental theorem of calculus, part B. You guys should have seen stuff like this before. If you have you're graphing, let's just say you're graphing y versus x, for example, and your graph looks like this. And then your task is to find out, well, what is the area under this graph right here from this x initial to this x final? So if you need to find out what is this shaded region right here, you could figure out the magnitude of that shaded region just by doing the integral of x dt. Okay, so that's all we're doing here. The area under a graph is given by the integral of this function. So y versus x in this case. All right, so let's go with this. Number 5 says the following. Let's figure out the change in velocity for segment A. And you know what? That's going to equal 0. So we're done with that. We're done with part A. The change in velocity for part A is 0 meters per second because A equals 0. The acceleration equals 0. So if the acceleration equals 0, then I guess,
Justin.
say again.
Oh, I'm sorry.
That's all right. If the acceleration equals 0, the change in velocity equals the integral of 0 times dt plus the initial velocity. Now, at this point, in this particular case, we can say the initial velocity is 0, which means, again, it starts from rest. Starts from rest. So that's why the change in velocity during segment A of that salamander tongue is it doesn't change velocity. It's moving. It doesn't mean it's not moving. It just means it's not changing its velocity. And I think it does start from rest. I would just flat out say it's starting from rest. I mean, because when you think about it, the salamander tongue starts in the mouth of the salamander, and it's just sitting there motionless at rest. And then all of a sudden, a fly comes into view, and the tongue then proceeds to go from some 0 velocity to some non-zero velocity. So that's my idea about salamander tongues. Let's talk about segment B. So number 6, what's going on with the change in velocity during segment B? And the answer is area under graph, because just to repeat, I did the heavy lifting to show that change in velocity is a times dt, which is for the umpteenth time area under graph. So let's figure out what the area under the graph is. For segment B, segment B is a triangle, and we know how to figure out.
Professor keeps kicking me out.
My guess is you just have an unstable internet connection. I mean, I'm not throwing you out. So you're probably just dropping a connection on your end. So maybe somehow like recycle your Wi-Fi or move to a different area or try a different device. Because there's nothing, I'm not doing anything on my end to boot you off. So see if you can make a change and have it work. And so again, that happens to me. I always just reboot my Wi-Fi, reboot my device, change devices, change location. So see if that works. So during segment B, you know what I'm thinking? Let me just maybe re-eyeball this again. So I'm going to go back and kind of just once again write it like this: V final minus V initial. That equals, you guys know delta. Delta V is final minus initial. Delta means change in. So I'm going to go kind of back to this notation. Delta V is integral of A dt, because all I did here now, I said I'm going to move this over here. So just to be pure, just to be a little bit more pure. All right, so what's the area under the graph? So the area under the graph is, I know it's a triangle. The area under a graph for a triangle is 1/2 base times height. So let's do that. This all of a sudden, this becomes a simple operation because you just need to know how to do the area of a triangle. So it's 1/2 times base. Now here is I guess I'll call this the base of my triangle. Here's the base of my triangle right here. From 10 milliseconds to 20 milliseconds, that's the base. Here's the height of my triangle from 0 all the way up to that value. From 0 to a subscript 1, that's the height. So again, this is my base. That's my height. So you can see from this graph, that this height value is equal to A1. And A1 is given as 115 meters per second squared. My numbers, not yours. You can see that this base, it starts at 10 milliseconds and it ends at 20 milliseconds. So this is going to be 10 milliseconds. So here's the area of that triangle, which is going to give me the change in velocity because of all of this calculus and physics conversation. 1/2 base times height. The base is 10 milliseconds. So I'm going to write 10 milliseconds as 10 e minus 3 because 10 milliseconds means 0.001. I'm sorry, 10. I'll write it like this. 1 millisecond is 0.001 seconds equals 1 times 10 to the minus 3 seconds equals 1 e minus 3. I use this e minus 3, so that's not natural log base c. It's just 1 e minus 3. E means times 10 to the, in this case, negative third. So 1/2 times base times height. My height here is A1, and A1 was given as 115. I got to do some units here first. Oops. 1 e minus 3 seconds. And I can't leave off units. That's too sloppy. So the units here is 10 e minus 3 seconds times the height, and the height is 115 meters per second squared. That's the answer. So let's do dimensional analysis, which is always a requirement. Seconds here cancels with one of the seconds here. So I do end up with meters per second, which is good because that's what I would expect to end. That's what I would hope to end up with. So then all I have to do is to get out my calculator and say, what is 1/2 times 10 e minus 3 times 115? And my calculator says 0.5 times 10 e minus 3 times 115 is 0.575. So that's the salamander's velocity, salamander's tongue velocity at the end of segment B, 0.575 meters per second. And again, this is delta VB. So 2 down, 2 to go. I can maybe pick up the pace a little bit since it's kind of just a repetition. Yes?
Isn't the 10e minus 3 for 1 millisecond?
10 e minus 3 is 10 milliseconds. 1 e minus 3 is 1 millisecond.
Oh, okay.
Right.
Yeah.
All right. So number 8. Number 8. What's the change in velocity during segment C? Same conversation. It's going to be the integral of 80. And you know what you could do, and this would be totally fine. Instead of just trying to find the area under the graph, you could just say, I'm going to just find this function. You can use, like, do you guys remember y minus y1 equals m times x minus x1? Remember, like 9th grade, 10th grade geometry or trigonometry? I guess it would be geometry or algebra. Anyway, you could actually figure out, you can figure out the function, you can figure out the equation of this line and then integrate. In fact, that's totally reasonable. I was going to say that actually might require less time, but it would require more time, but it would be totally fair. So now I'm looking at segment C. Here's segment C. And to me, this looks like a trapezoid. And I know how to deal with trapezoids because you're going to be given a function. I mean, you're going to be given a table of equations on exam 1. So you don't have to worry about memorizing equations like this. I mean, the name of the game is to problem solve, to creatively cough up solutions and design interesting stuff versus memorizing the equation of a the equation of a trapezoid. So I need to find out this area right here that I'm cross-hatching in gray. What is that area? It's the area of a trapezoid. And again, I would give you the formula for the area of a trapezoid. It's 1/2 times height 1 plus height 2 times base. So here's height 1. Height 1 is right here. This is height number 1. This is height number 2. So this is H2. This is H1. And then this is base. So again, you can see the base is again 10 milliseconds. So now that we know those measurements for this trapezoid, it's going to be 1/2 times height 1, which is A1. A1 corresponds to height 1. And for me, that's 115 meters per second squared plus A2, because A2 is referring to height 2. So A2 in my case is 410. I'm factoring out the units because they share common units. So this is just meters per second squared. 1/2 base times height, or I'm sorry, 1/2 H1 plus H2 times base. And my base is once again 10 E minus 3 seconds. So we can do dimensional analysis, seconds. So once again, I end up with meters per second, which I would hope. And then my calculator says 0.5 times 115 plus 410 times 10E minus 3, or 2.625. 2.625 meters per second. And that's the change. I'm not saying this is the salamander's tongue velocity after segment C. I'm saying that's the change in velocity. Big difference. Okay, so let's highlight that.
Professor,
Yep.
wouldn't it be so much quicker to do this problem if you just did the integral?
No, it wouldn't, because you would be, first of all, let me say, you could do it that way, but if you want to actually do the integral of a function, you actually have to cough up the function itself, which is probably a bit more time consuming. So instead of saying no, I would say, yeah, it's the same. It's probably 6 one half versus 6 another. You know, in my case, so what I really want to do here is I really want to stress the fact that I really want to stress the fact that the value of an integral corresponds to the shaded area under the graph between two boundaries. That's why I'm specifically doing it this way.
They didn't give a function, so that's also why.
Say again?
They didn't give you a function.
Yeah, it didn't give you the function, so you could actually create your own function. You have enough information to create your function. That's just pretty time consuming, but it's not, and it's also not the point I want to stress in this problem. I want to stress this: the integral. This integral is the area under this graph. So, but what you, if you unless I specify to do it a particular way, you always have your choice of solutions as long as you explain yourself. So the last one, change in velocity for segment D. Here's segment D, one more to go. Here's segment D. So this is a triangle again, and I know how to calculate the area of a triangle. This is the triangle I'm after. This is the triangle corresponding to segment D. Wait a minute. Okay. Okay, there's spending some time on a triangle here. Okay. So this shaded area corresponds to the integral of a dt. So again, this equals area equals integral of a dt, which again happens to be the integral of a dt happens to be the change in velocity. So this is definitely a mixture of math and physics and salamander tongue. So the change in velocity for segment D is the area of a triangle, 1/2 times base. The base is yet again 10 milliseconds, 10e minus 3 seconds. That's the base, 1/2 base times height. The height is A2, and for me, A2 is 410 meters per second squared. So let's cancel those units, dimensional analysis time. 1 seconds here, cancels with one of those seconds. I do end up with meters per second, which again is what I'm expecting. And my calculator says 0.5 times 10 e minus 3 times 410 is 2.05. 2.05 meters per second. That's not the velocity of the salamander's tongue. That's the change in velocity of the salamander's tongue. So I am done with the components, and all I have to do is add up all of these changes. So number 10, the velocity is just, as I said before, I'll just make a little copy and paste here. I'm just going to recycle my starting out position. Okay. I'm going to reuse this. And I have all of these values sitting here. So I'm going to add them all up. So 0 plus 0.575 plus 2.625 plus 2.05 equals 5.25. And we are done. 5.25 meters per second. This is the answer. This is the velocity. And again, technically you could say, I guess to be hyper precise, this is the change in velocity of the salamander's tongue at the end of this interval. And because the salamander's tongue is starting from rest, this is the velocity at 40 milliseconds. So this is us talking about acceleration. There's a lot to like about this problem. There's 3 or 4 major takeaways from this problem, and in no real order. Again, we're talking about fundamental theorem of calculus, which is this. The area under a graph corresponds to the integral. And the definition of acceleration, that's good to know. And then doing this calculus operation, that's good to know. And I guess that's kind of it. This thing that I'm doing here, when you break things into steps and solve each step separately, and then add together the contributions, this is called superposition. So superposition means to do exactly what I did. It means to take a challenge and break it up into multiple chunks. So superposition is part of this. So that's a lot. That's a lot of good stuff here. What time is it? It is now 2:49. So I can go ahead and get quiz 4 ready. Quiz 4 is 270. Give me a couple minutes.
Will you allow some time after this lecture to do any of these quizzes?
Yeah, I'll allow time when we're done and reopen past quizzes so that if you need to go back and do something, you'll have time to do that. All right, so give me a moment to get chapter 2 quiz 4 ready. Chapter 2 quiz 4. Chapter 2 quiz 4 is problem 70. Problem 70. 70 says two particles move along an x-axis. Okay. Okay, so let me make that available. Again, it's 251, let's say 330. Okay, I think you should see it. I think you guys can now see Chapter 2, Quiz 4. Our fourth quiz and fifth overall assessment for today. Chapter 2, Quiz 4. Let's do this. Okay. Kinematics. Once again, this is, well, I mean, to be honest, you guys, you know what this really is? This is one-dimensional kinematics along with calculus, along with clever thinking. Okay, so those are the three ingredients. One-dimensional kinematics, calculus, and clever thinking. Two particles move along an x-axis. So here is, and let me make sure I'm sharing. Again, a lot of times I'm talking, I'm rambling, ranting, and I haven't shared my screen, so make sure to stop me. But here's an x-axis. Stop me if I'm doing that. Here's an x-axis. Two particles move along an x-axis. So, well, here's one particle. Here's another particle. And a key, really, you guys, a key to this is just reading the question over and over again. Two particles move along an x-axis. So this is my x-axis. Two particles move along an x-axis. Particle one has its motion control. So it's exhibiting, it's undergoing program motion. So you as a engineer or a tech person would program this red particle to move according to x equals 9t squared plus 7t plus 2. And the acceleration, this is a little bit of a twist. The acceleration of particle 2 is a equals negative 9t. So collectively, this would be expressed in terms of meters, and this would be expressed in terms of meters per second squared. So that's pretty interesting. Position function and a acceleration function. It says when the velocities of the particles match, what is their velocity? So number one, here's the velocity. Here's the velocity of object one, of number one. The object of one. Object one is velocity is the time derivative of the position function. And I know how to take the derivative of this position function because the position function is 9t squared plus 7t plus 2. And I know the power rule, and I know that velocity function is v equals 18t plus 7. And again, v, and I'll use v subscript 1. This is the velocity function for object 1. Here's velocity of object 2. Velocity of 2. And this is different because I don't know position. I don't know the position function. I know the acceleration function. And I know that acceleration is dv dt. So I'm going to have to go through these operations. You've seen this before. Multiply both sides by dt. So I have dv equals, once again, a times dt. That's good to know. So I need to get my velocity function. So I'm going to integrate the left side. I'm going to integrate the left side, and I'm going to integrate the right side. Whatever I do to the left side, I have to do to the right side. So and I better specify limits of integration or my boundary conditions. Okay, so this is from some initial velocity to some final velocity, some initial time to some final time. So here we go. I have the integral of dv is v. If I evaluate v from initial to final, I get v final minus v initial equals the integral of a acceleration. And my acceleration function is minus 9t times dt from some initial time to some final time. So let's keep going with this. V final minus V initial equals, what's the integral of negative 9t? It would be negative 9t squared over 2, sorry, which equals negative 4.5 t squared. So that's it. So you know what I have? I have V final, and again, I'm just gonna replace V final with just V, regular old V. But maybe I better do a subscript 2 since I am talking about the velocity of object 2. So the velocity of object 2 as a function is going to be negative 4.5 t squared plus its initial velocity. That's it. So let me make a big deal about both of those functions because we have to set them equal to each other. This is the velocity function of object 1. This is the velocity function of object 2. Okay. What else do I need to be aware of? It says the acceleration of particle 2 is given by this function. And at time equals 0, its velocity is 24. So that answers that question. So really, my truly updated velocity function should be this, since I do know the initial velocity. So I'm going to have the velocity of particle 2 is going to be negative 4.5 t squared plus, when time equals 0, the velocity has a value of 24 meters per second. So really, this is my velocity function for particle 2. All right, so that is what we have to match with velocity 1. So let me erase that. That's good. All right, number 6. What is the velocity when they match? So when velocities match, basically that's saying V1 equals V2. That's what happens when velocities match. What is the velocity when the velocities match? Well, I don't know. Let's just keep going. So here's V1. My velocity function for particle 1 is 18t plus 7. Here's velocity 2. Negative 4.5 t squared plus 24. Is that right? Yeah. Okay, I think so. Plus 24. So once again, just for the sake of double checking, this is V1 must equal V2. We had to do some work just to get that expression for V1 and even more work to get that expression for V2. So number 7, let's find the time when this happens. Find the time t when this happens. Okay, so I'm seeing a quadratic equation. And I'm going to get it in final form for the quadratic. So I guess I'm looking at step 7. Step 7, if I arrange it the way I need to arrange it for a quadratic equation, it's going to be 4.5 t squared, moving this over to the left side, plus 18t. I'm going to move 24 from the right side to the left side, so that would be minus 17. Okay, equals 0. So you guys should know how to do this on your calculator. I mean, here's the worst case. You guys know that t equals minus b plus or minus b squared minus 4ac. So this would be the worst case scenarios. You literally use the quadratic formula. That would be enormously time consuming. Well, not really. That would be time consuming, not enormously time consuming, but it would be time consuming and it would open you to error. So use your calculator or do the quadratic equation. What I'm going to do it on my calculator, but I'll just use this little applet here. It's like another handy dandy. I'm going to ask the salamander to do this. I'm going to do a quadratic calculator. And here's one called math.com. So I'm just going to use this. What I'm doing here, you would do on your calculator or the quadratic formula. But for me, I got to check. My squared term is 4.5. So my squared term is 4.5. My linear term is 18t. So I got 4.5 t squared. So that's where I got the 4.5 from, plus 18t. 18 is the coefficient of that linear term. Linear means the exponent is 1. So this would be 18 right here. And then my constant term down here, which means there's no variable, is negative 17. Negative 17. All right, so here's my quadratic equation. So that's my answer. I'm getting this answer. I'm ignoring that negative value since there's no such thing as negative time in this context. So this is the time at which my calculator, my quadratic equation spit out the time at which these velocities are equal to 0. And this is the number right here. T equals, let me make that easier to read. There, right there. So I know at this time the velocities equal 0. So I can just I'll make that note. At this time, V1 equals V2. Okay. So what is V1? Should I calculate V1? Here's the expression for V1. Should I use V1 or should I use V2? The answer is it doesn't matter because they're both going to be equal to each other at this particular time. So I'll just use V1 since it looks simpler. So V1, which is also going to be equal to V2, is going to be 18 times T, 0.7888665, on and on and on, seconds plus 7. So let's go ahead and do 18 times 0.7888665. 755 on and on and on plus 7 or 21.1996. That's the answer, meters per second. And this is the answer. When V1 equals V2, they both equal 21.1996 meters per second. So good problem. Some new stuff. These problems they're all kind of similarish, or there's a lot of similarities, but these problems are definitely introducing new stuff. That's it. That is it. That's quiz 4. Let's do this. I need a 7-minute break, actually. So I'll see you guys at 3:12, and then we'll finish up, and I'll leave time on the back end. So I'll see you guys at 3:12, 312, 3:12, where I'm taking the opportunity to also introduce or reinforce. I should say reinforce some stuff because you should be introducing yourselves to the background material through the lecture videos and completing the green sheets. Okay, so it's an arcade video game. All right. In an arcade video game, the spot is programmed to move across the screen. So this reminds me of the game Pong. Pong, and I think Pong was the world's first video game. Pong. In fact, just because I'm curious now, Pong. Pong. Yeah, there it is. There's Pong. Look how exciting. I remember playing this. I am old enough to remember when Pong was really popular. This was definitely ground changing. Look at that. Look at those realistic graphics. I don't think you need a GPU for that, but anyway, let's solve this video arcade problem. So I'm going to draw a video screen. Here's my screen. And again, just know this on the exam. So what I'm doing here now, like what I'm showing you is pretty darn consistent with what you're going to need to do on an exam. You're going to have to follow some more specifications, and I'll talk about those, but just get in the habit of like really explaining what you're doing, meaningful explanations, not like, now I'm going to use this equation. Now I'm going to plug this number into this. Those are not meaningful explanations. So that is the secret, meaningful explanation. So here's my video screen. Here's my spot. It says in this video game, a spot is programmed to move across the screen according to, again, a special function. So this is, you program this as a video game. Video game programmers, not all of them, but a large percentage of them are like very proficient with physics. And when you think about it, you kind of have to be, to model motion and forces and repulsion and do all sorts of like radiosity algorithms for photorealistic rendering. So this position function is 11.7 t minus 0.659 t cubed. And this position, I'm going to call this is my initial x position. It equals 0. And then at the far side, that's my final x position. And for me, my number says 23 centimeters. 23 centimeters. And look, here's sort of the game conditions. When the spot reaches a screen edge, and where do you find screen edges? This is one screen edge. This is another screen edge. So if that red dot encounters a screen edge either at the far right side or maybe again as it returns on the left side, then the game restarts. When the spot reaches a screen edge either at 0 or 23 centimeters, time is reset to 0 and the spot starts moving again. So it resets. Okay, at what time after starting is the spot momentarily at rest? Let's do that. So that, I think that's just going to be easy. Once again, the calculus definition of velocity, instantaneous velocity, is this the rate of change in this object's position. That's all a derivative is. It's the rate of change. In this case, it's the rate of change of position with respect to time. So our job is to take the first derivative of the position function, which is 11.7 t minus 0.659 t cubed, and we can do that. That equals 11.7 t. Oh, that equals 11.7 minus 3 times 0.659 t squared, and then let's evaluate that at what time after the starting point is it momentarily at rest. So all of this, whatever this is my velocity function. So the question is, when does this velocity function equal 0? Because when the spot is at rest, it has 0 velocity. So number 2. So apparently 11.7 equals 3 times 0.659 t squared. So let's get a value for t. So t equals, I guess, the answer. So let's do 11.7 divided by 3 divided by 0.659, 2.432. And I'm going to store that. I think I might need this again. Maybe I do, maybe I don't, but this is 2.4327 seconds. So I'm going to write down SICM, memory location A. I'm storing this in my calculator's memory location because once again, SICM stands for store in calculator memory. Just in case I need to reuse this. So store alpha A for me. Okay. And that's the answer to part A. So we are done with part A. Done with part A. Part B says, at what value of X does this occur? So this seems kind of oddly easy because we're just evaluating this X function. So X at this time. So X parenthesis, calculator memory location, A close parenthesis, X at that time is just going to equal 11.7 times that time, which is, again, stored in my calculator memory. 11.7 t minus 0.659 t cubed. And that will be the answer. So let's do 11.7 times t minus 0.659 times t cubed, 18 and some change. $18.975 and some change, 18.975 meters per second. No, meters. And that's the answer to part B.
Could you scroll down so that I can see?
Like that?
Thank you.
Okay. Part C. What is the spot's acceleration when this occurs? So still pretty easy. I know what I'll say again, once again. Acceleration is the time derivative of velocity. So when I write dv/dt, what I'm really saying is I'm interested in finding out the rate of change of velocity as a function of time. So let's go ahead and take the first derivative of the velocity function. And the velocity function is 11.7 minus 3 times 0.659 t squared. And where did that come from? Let me just make this notation. We did that work up here. We did this work right here. This is V. This is my velocity function, which again happens when you take the time derivative of position. So I know how to take this derivative. It's going to equal -2 times 3 times 0.659 times t. And then at t equals what I have stored in calculator memory location. At what value of X does this occur? At what value of X does what occur? And the point is, and it's saying, at what value of X does the spot come to a rest? So this is T sitting there in my memory location. I got that answer from A. So if I plug all of that stuff in, -2 times 3 times 0.659 times alpha A is, let me try that again because I didn't have that stored the way I did. All right. So -6 times 0.659 times. Okay. Negative. Oh, this is acceleration. Okay. Negative 9.6. I have to back up and revise my explanation. Negative 6.189 and some change meters per second squared. And this is the answer to part C. Oh, and I said meters, you know, I need to change that. And this is the answer to part C. We're working in units of centimeters. So everything they gave us was in terms of centimeters. So let me go through and just make these very obvious changes. That's not centimeters. I'm sorry, that's not meters per second squared. It's centimeters per second squared, just like over here. This is 18.975 centimeters. And I guess everything else is okay. So just making those corrections. We're done with parts A, B, and C. And part D is the last step. At what time greater than 0 does the spot first reach a screen edge? Well, let's talk about that, because from part B, I know for a fact that my spot never reached the far right edge. So my spot made it to about there. My spot made it to that location. And at that location, it came to a complete stop. And then it reversed itself. So it made it all the way to 18, with my numbers, 18.975 centimeters. It stopped and then it reversed itself. And how do I know it reversed myself? Because my acceleration is negative. So that's how I know. This negative means acceleration is oriented in negative x direction. That's what it means. That's what that negative sign means. I have my acceleration vector is doing this. So let's just look at an intermediate position. Let's just say I'm looking at my dot, and it's like right here, just for the sake of conversation. Some, again, intermediate position. Let me get rid of this since it's cluttering up. Okay, so at some intermediate position, the dot itself is still moving forward. So the dot itself still has a velocity going in that direction. But you know what? All the time, even though the velocity is going to the right, it's slowing down because I know my acceleration is going in the negative x direction. So this green vector, this green arrow, is my acceleration vector. This purple arrow is my velocity vector. And you can see they're pointing in the opposite directions. The direction of acceleration is in the opposite direction of the velocity. And you know what you call this? You call this slowing down. This is, come on, slowing down. When you have acceleration and velocity opposing each other, that is called slowing down. So that's why this particle does slow down. Eventually it comes to a stop. And then because the acceleration is still in the negative x direction, it reverses itself. The dot reverses itself and heads back towards the left side edge. So that's how I know. That's the thought process that's going on in my head that says, hey, this dot is going to the right and then it's slowing down. So it's going to the right, slowing down, coming to a stop, and then it starts to, and then it starts to speed up, and then there you go. So I know that the first edge reached by the dot after it's launched is once again at x equals 0 because it never made it. It never made it to the 23 centimeter mark. So step number 5 is basically doing the math and physics to support what I think is going on. Okay, step number 5. So once again, the spot returns to the edge of the screen at x equals 0. They didn't tell you that, but we actually had to figure that out using all of this thought process. So let's see, x once again equals 0. So x equals 0 happens, there's x equals 0, and x is also equal to 11.7 t minus 0.659 t cubed. So this is what we need to do. We need to find out the time. I guess that's all we have to do. All right, so that's it. Solve for t. Solve for t, number 6. So let's solve for t from that. I'm going to get, I don't think I have to write down anything more. 11.7. $4.21 and some change. So that's the time at which the spot returns to an edge. And this is once again the x equals 0 edge, 4.213 and some change seconds. That's the answer to part D, which is it. That's it. So I don't know. In many ways, you guys, not much new here. Just it's a different type of problem. And again, the thinking is you can be completely in the dark about how to do physics, even though you've had physics classes before this one. Even now, you can be completely in the dark, and all you have to do is digest all of these solutions, which is not at all impossible. It's not even that crazy. Digest all of these solutions, and you're going to be good to go. When you see a problem, that is a brand new problem. I know, easier said than done, but it's doable. I just finished a class on August 2nd where literally half the students 4-pointed the class. So it was pretty unique. I think that was like the best performing class I had. And there's reasons why, I think, but I don't think anyone killed themselves trying to like do well I think they all studied hard. They all had good discipline, but anyway, that's this problem. That's our fifth. Let's do one more quiz. Well, maybe one or more. It's only 3:30. Really seriously get committed to the lecture videos. You need to watch them repetitively over and over again, and make sure you write down the list of questions that you have. These videos should be clear from start to end. You need to fill in the green sheets. And as you fill in the green sheets, learn, make sure you understand everything that you're writing down. You need to re-watch Zoom classes, and you need to take advantage of tutors. So visit tutors, and you office hours. You need to take advantage of office hours. And yeah, I mean, there is. I was just kidding before. On Thursdays, we can talk about, we can do some of this stuff on Thursdays, but now keep in mind, that's not really Thursday. We can spend time on Thursday. So I'll just say Thursday time. Your requirement or your expectation is watch the lecture videos many times, fill out the green sheets very thoughtfully, rewatch the Zoom classes, visit tutors, chat with me via office hours, and then maybe sometimes, but Thursdays are pretty packed up. So we don't have a lot of spare time on Thursdays because we're doing labs, demonstrations, and simulations. So keep all of this stuff in mind. You need to, and then also on Thursday, I'm going to pass out sort of like a management sheet that helps you track your status in all of these areas. So I don't know how many of you guys have had a class like this. I've had a lot of, I think literally I was probably a junior myself in college before I had what I would call a professional type of class. I make the difference between professional and academic classes. Academic classes are just like school, and this is school. But I treat this, I think of a class like this as a professional class because you actually have to be organized. So that's just my terminology. All classes are equally important and they're all professional, but I'm just using terminology like that because it helps me make a contrast. So, all right, that was quiz. That was quiz 5. So I guess we do quiz 6. Let me get quiz 6 ready. Quiz 6.
Could you? Oh, never mind. Could you show the screen for
Yeah.
quiz 5 again?
Yeah, this one. Actually, let me take a screenshot. Okay. Quiz 6. Okay. $686. Motorcycles. Okay. It's now, the time is now 3:36. So. All righty then. Last quiz of today. This is the chapter 2 quiz number 6 assignment. Chapter 2 quiz 6. Let me know if you're not seeing it in Wiley Plus. And this is it. Our last quiz problem, and then we'll come up for air and see who needs a bit more time or has questions about past quizzes or that Desmos assignment. A motorcyclist who is moving along an x-axis. So once again, that's your cue. Because on the exam, I'm not going to say, hey, the following is a one-dimensional kinematics problem. You're going to have to know. And so this is a cue. A motorcyclist is going along the x-axis. So right here, this is saying, aha, one-dimensional kinematics. Not X and Y, not X and Y and Z, but just X. A motorcyclist is moving along an x-axis towards the east. So here's my motorcyclist. There's my motorcyclist. Here's my velocity. It's moving towards the east. So this way's east. Okay. The acceleration of this motorcyclist is given as stated, A equals 6.3 minus 1.2 t meters per second squared. Okay. For t between 0 and 6 seconds. At t equals 0, the velocity in the position. So I'm just gonna write this down. So here are my initial conditions. They tell you the initial conditions, but they're telling you in sophisticated terms. I like simple terms. So here are the initial conditions, according to the problem statement, I'm looking right here, at t equals 0, the velocity and position of the cyclist are 3 and 7.3. So I'm going to just record that. Just take what's given to you and record it. So at time equals 0, I have my initial velocity is equal to 3 meters per second. And my initial position, x subscript I, my initial position is 7.3 meters. So part A is what's the maximum speed by the cyclist? So this is this should kind of maybe ring a bell. So I know from calculus, let's just say that I have a graph. I know from calculus, so I have just a generic graph right here. And let's just say this is a graph of velocity versus time. And it looks something like, I don't know, it looks something like that. You know where the maximum velocity is. The maximum, because we're trying to find the maximum velocity in part A. What is the maximum speed, which in this case would be the maximum velocity. I'm just not caring about the direction. So right at this black dot, that black dot is showing you the maximum velocity because that's the very peak of that curve. So all I need to do is draw a tangent line at that point and just have it go all the way. And there you go, right there. This value, let me move this down. Okay. This is V max. So this point, V max. And you can see graphically, you can see, yeah, that is the maximum velocity attained by the motorcyclist right there. So what's true about that tangent line? This is a tangent line. It's tangent to that maximum point. And I know this. I know that for a tangent line, the slope of a tangent line at this Vmax, at Vmax equals 0. You can see this is a purely horizontal. This is a purely horizontal line, which is the only line you could use. So you're taking a purely horizontal line, you're using that as a tangent. You're saying, where exactly is this purely horizontal line just nicking my velocity versus time curve? And at that point, at this nicked point, that's your Vmax value. This is a purely horizontal tangent. And I know purely horizontal means slope equals 0. So what's the slope of this graph? Well, I guess, what is the slope of this graph? Well, slope, let me do this. M stands for slope. And you know that slope is rise over run. And you know, generically, you've probably seen this a lot of times as well. Rise is the y-axis, so it's delta y over delta x. That's true generically, but here, it's not delta y because our y-axis, we're using v. So instead of delta y, I'm writing delta v because, again, we are using very specifically a velocity versus time graph, but it's the same thing. All right, and then run is delta x. What's delta x in this representation? It's delta t. So now what I'm going to do, one more step. So this is slope, m equals slope. And from a calculus point of view, so instantaneously, which means for delta t approaching 0, I'm going to have this. I'm going to say dv dt, not delta v over delta t. It's dv over dt. That's still equaling the slope. And for that horizontal line, this slope must be equal to 0. And if that's not incredible enough, dv dt equals acceleration. So this dv dt right here, dv dt is, again, acceleration is defined as dv dt. So all I need to do is find out when acceleration is equal to 0. So that's my big breakthrough. Number 4, aha, breakthrough. So based on all of that conversation, and you guys, when you practice enough, this conversation that I'm taking 25 minutes to get through, you're going to know like in a minute. You're going to have to just think about it briefly. And that's what practice will do to this, to you. A breakthrough, set acceleration equal to 0, and find t, and then find, after you find t, find v. That's the game plan. So number 5, here's acceleration. Acceleration equals 6.3 minus 1.2 t, collectively meters per second squared. Okay, and to set it equal to 0. So when is the acceleration equal to 0? The acceleration equals 0 right here. So right at this point in time, the velocity is not changing. And in fact, the acceleration is literally flipping from some positive value to some negative value. So before this inflection point, this is positive acceleration. Acceleration is greater than 0 here, but after that inflection point, acceleration is less than 0. So right between that transition, you have acceleration equal to 0. The particle is momentarily stopped, and that happens at t equals something. So what is 6.3 divided by 1.2? 6.3 divided by 1.2 is 5.25. That happens at 5.25. 5.2 seconds equals time when cyclist is momentarily at rest.
How did you get that 5.25?
From step 5. Look at step 5.
Oh, okay. Thank you.
Yep. Okay, that's not my answer because again, my game plan said take that time and find out the velocity. Okay, so V equals, again, I'm going to go through sort of the rudimentary part. Let's see, if acceleration is defined as dv dt, then I can say dv equals acceleration times dt, just multiplying through by dt. And now I got to integrate again. So I'm going to do integral, number 7, number 8. And I better specify my boundary condition. So this is some initial velocity, some final velocity, some initial time, some final time. All right, so if I process step number 7, I'm going to get V final minus V initial equals A. And technically it's going to be A. Oh, let me actually, sorry, I got to equals the integral of A, which is 6.3 minus 1.2 t dt from some initial to some final. And I know what the initial is. 0 seconds is the initial time, 6 seconds is the final time. Let's keep going. Number 9. So V final minus V initial equals I need to integrate that expression. So I have 6.3 t minus 1.2 t squared over 2. And again, I'm evaluating from 0 seconds to 6 seconds. Let's keep going. Number 10, I'm running out of room. Number 10, V final, which is in this case is my final velocity, my velocity at this point in time at 5.25 seconds equals 6.3 t minus 1.2 over 0.2 is just 0.6 minus 0.6 t squared plus v initial. I'm bringing this v initial over to the right side. Okay. And I think this is the last thing I'm going to write down. Let's see. That velocity, the velocity at 5.25 seconds, which is the maximum velocity, because we're saying over here, this is 5.25 seconds. So here you go. You need to do 6.3, and yes, shout out if you see me making some mistakes. 6.3 t minus 0.6 t squared plus the initial velocity. And the initial velocity is at t equals 0, the velocity is 3 meters per second. So that 3. Okay. I guess that's it. Okay. And then evaluate this from 0 to 6. And let's get an answer for the maximum velocity. V equals V max at that 5.25 second mark. Now we're going to figure it out. Okay, 5.25. Just maximum speed. Oh, hang on. What is the maximum speed? So let me, I got to back up. I had my eye on part 2. So pardon the interruption. So acceleration V max, 5 is good. 6 is good. 7 is good. 8 is good. 9, I'm not evaluating this across that interval. Here's the change I need to make. I'm evaluating this at t equals 5.25. Because again, I just kind of jogged myself into sanity. I kept saying, well, we just got done showing that the velocity reaches a max value at t equals 5.25 seconds. So I need to make that change in step 9. I need to make this change in step 11. And then now you're good to go. So again, I was kind of looking ahead at part B. Okay, so let's see how this goes. Okay.
What's your upper limit?
There is no upper limit. I'm not integrating, I'm differentiating. That's why, again, let me just go through that again. In step 6, in steps 1 through 6, I basically show that at 5.25 seconds, right here, I reach an inflection point for this velocity. This inflection point happens at the max value based on all of that conversation that went into steps 1 through 6. So step 6 says your max velocity happens at 5.25 seconds. 7 is good. 8 is good. Step 7 and 8 is step 7 and 8 is me basically getting a velocity function. Okay. So that's all step 7 and 8 that I have my velocity function. Ultimately, I have my velocity function here in step 10. And then I'm saying, okay, if this is my velocity function, what is the velocity function at 5.25 seconds? Because at that time, that's my max velocity. And that's what we're being asked to solve for. So I know I didn't help matters by making that little misstep, but better late than never. My calculator says 19.5375. 19.5375 meters per second. This is the answer to part A. And I think all of this is good.
Wait, so to get that number, what did you do to get that 19 number?
I did step 11.
But you didn't plug it. You have a t value. You just plugged in the 5.25 for t. That's all you did.
Yeah, when you see this designation, it means take this polynomial and then use this value of t here and use this value of t here. Because once again, this is my velocity function. And I want to know, what is this velocity specifically at time equals 5.25 seconds? So that's typically how you designate, or you specify that task in this manner.
Gotcha.
Okay. So that's part A. I know this motorcyclist hit a peak velocity of 19.5375 meters per second. Part B says, what's the total distance? And again, this is where I got screwed up because I was taking my eye off the ball. So step 13. Step 13 is part B. And part B is saying total distance. So what's total distance? I'll just write it like that. Total distance traveled by this motorcyclist from 0 to 6 seconds. Total distance. Total distance equals $sign. $sign is the money variable. That's the variable I'm after. So step 14, here goes. I know that the definition of velocity is dx dt. And I would write this as definition of instantaneous velocity. You can't just write down formulas. You have to say something about them. Instantaneous velocity. That's the definition of instantaneous velocity. So I'm going to do what I've done before. I'm going to multiply through by dt. So dx can be written as v dt, and I'm going to integrate both sides because I want to find out what is this total amount of motorcyclist distance traveled. So integrate the left side. Anything you do to the left side, you must do to the right side. So here's my left side, step 16. Boundary conditions. X initial, X final, T initial, T final. We know all of those. All right, so what's the integral of dx? The answer is x. So if I evaluate x across x initial to x final, I get x final minus x initial equals the integral of my velocity function. Here's my velocity function in step 10. So there's my velocity function. I'm going to take the integral of that 6.3t minus 0.6 t squared plus 3. That is my velocity function that I need to integrate from t equals 0 seconds to t equals 6 seconds. That's initial and final. 17 x final minus x initial equals 6.3 t squared over 2 minus 0.6 t cubed over 3 plus 3t evaluated from 0 to 6. From 0 seconds to 6 seconds. And did I do that right? 6.3 t squared over 2 minus 0.6 t cubed over 3 plus 3t. I think that looks okay. All right, so at this point, you're good to go because you know x initial. X initial right here, 7.3. So you know your value for x initial. You know how to evaluate this function between 0 and 6. So go ahead and let's solve for the total distance traveled by this motorcyclist from 0 to 6 seconds.
Wait, I'm sorry. You said t equals 0 for that x1, but then you also circled the x1 equals 7.3.
The x initial is 7.3 meters. And then T, you're evaluating T from 0 seconds to 6 seconds because that's what the problem specified. What is the total distance traveled by the motorcyclist between 0 and 6 seconds? Okay, so let's do 6.3. Oh, oops. A little slight correction. Sorry. Let me just hold off on that and hold off on this. I forgot to bring the X initial over to the other side. So let me bring X initial over to the other side. So now this is what I'm going to figure out. Number 18. Total distance traveled by the motorcyclist is this. 6.3 divided by 2 is 3.15. So it's going to be 3.15 T squared minus 0.2 T cubed plus 3T plus X initial, which is 7.3 evaluated from 0 seconds to 6 seconds.
If he's at 7.3 at t equals 0, then wouldn't x initial, like, wouldn't you not add that because he's not traveling that during the time period?
But you're looking for, that's basically the head start. This motorcyclist started off at a head start of 7.3 meters. So you have to factor that into the net distance traveled. 3.15 times 36 minus 0.2 times 6 cubed plus 3 times 6, 88.2. Okay. X equals 88.2 meters. This is part B. This is the total distance traveled by this motorcyclist during this interval. So that's the answer to A and B.
Why did you change the 0 to 6 to 6.5 and 0.5?
6.5, 0.5.
In number 18, the very last thing that you have written. Maybe I can't read those right, but what are those numbers?
Like right here,
Yeah.
that's 0 seconds and that's 6 seconds.
Oh,
It's the boundary conditions. Right. Okay. That is it. That is 6 quizzes and 1 Desmos exercise. It's now 4:03. So let me just take a look at the grade book. I'm curious to see how people are keeping up. There's one thing I've kind of noticed that sometimes the students kind of falls behind, slips behind, and never really speaks up. So that's kind of ripe for change. Grades for our section. All right, so let's see.
Hey, Professor.
Yeah.
Could you kind of explain adding in the 7.3 because I forget, or like I did what you did at first and didn't use that extra, or I didn't add in like that meters where he starts, and I got it right. So I want to know like if that was just a freak accident or if it could both ways.
Well, I guess that would be a question I would just turn right around on you. Why do you think that would be right? And right now you're thinking, I don't know, but think about it. Go back to step 17. Step number 17. Yeah, I could see, like, so you did X final minus. Okay. So let me see. Would that give you the same result? 3.15 times 2. Yeah, the only problem I had with my original work is that I need to bring X final. I'm sorry, I need to bring X initial. I need to bring this variable right here over to here. And then once I do that, then at this point, I evaluate the whole thing, this whole expression. So this whole expression includes this term, which is the initial position of the motorcyclist. So I kind of have to do it this way. I'm not sure how. I'd have to think on that a bit. I'm not sure how or why you would get the right answer if you did it any other way.
Is it because, sorry, real quick.
Oh, that's
Is it
fine.
because when you put the 6 in, you get 95.5, and then you have to subtract the 0, which leaves you 7.3 at the end, which then gives you 88.2.
Yeah, so you're saying when you well, when I do this, when I add up all of this, when I add all of that, I get 3.15 times 36 minus 0.2 times 6 cubed plus 18 plus 7.3. Yeah, I think you're right. I think you're right. You're right. So you could.
Yeah.
You're right. You're right. So I really didn't have to backtrack. I just did it because it looks strange. Anyway, that's just a personal preference for me. But you're right. Either way, you're going to get the same answer. You're right. Okay, so that's good. So looking at the grade book, quiz 1, quiz 2, quiz 3, quiz 4, quiz 5. So not everyone is done. Well, still a good number of you are working on quiz 6. All right, so what I will do, I'll hang out here because it's only 4:07, and goodness knows we can't ever end class earlier. But I'm going to just wait here. I'm done with my part. Solving 6 problems in a Desmos assignment's a lot of work to do in one day, especially day number 1. So you guys keep working on quiz 6, and then does anyone need me to reopen any prior quizzes?
Yeah, I need quiz 3, 4, 5, and 6.
Can you open 1, 2, and 3?
Wait, did I heard 3, 4, 5, and 6?
Correct.
And 1, 2, and 3. Those are the only ones I need. 1, 2, and 3.
Ah, okay. That's a lot of quizzes. So, I mean, here's the thing. I mean, it's fine to today, but if I'm opening all those quizzes, 3, 4, I mean, I guess my question is, what were you doing while we were solving quizzes? And maybe you were having tech issues, which is fine. But I'm just saying, going forward, fix whatever technical issues you have, and don't let yourself get too far behind. So again, today, yeah, if you were having connection problems, that's fine. We can deal with it. But just going forward, I at the end of a class, I can't be reopening like 2/3 of all the quizzes during the last half hour. So, but I understand it's day 1. I just wanted to make those points for going forward purposes. All right. So, I guess what I'll do, I think, because everyone wants kind of all these quizzes reopened. It's 4:08. I'm going to reopen all of these quizzes until 5 p.m. So your job is to finish all of these quizzes one way or the other between now and 5 p.m. And if you're going to look at, I hope if you're completely done with everything, then yeah, either way, you can drop off whenever you feel like it. 3, 4. 1, 2, 3, 4, 5, 6. 1. Done with quiz 1. Quiz 2. Quiz 3. Quiz 4. Quiz 5. Okay, all quizzes are now available until 5 p.m. And I'll hang out here until 4:30 so we can chat if need be.
Do you think you could go back over how to submit the Desmo screenshot?
Yeah, log into Blackboard. So let me go there with you. So log into Blackboard. Go into our class, section 145, 113, and then you're going to click on course documents, and it's chapter 2, Desmos exercise number 1, and that's where you attach your work. And your work has to basically look like this. Let me share it. You need to have your position function, your velocity function, and your name. So it's name, and then position function, then velocity function. And that's, you screen capture that into a file and you attach that file to that link in Blackboard. So
When I go to course documents, it says there is no content to display.
yeah, let me just extend, let me reopen it.
Okay,
Right,
thanks.
so yep, I'll reopen this until 5 p.m. And it is now done. Let's see. Okay. There, now everything is reopened until 5. All right, now again, hang out till 4:30 or longer if need be. And here's my notebook.
Hi, Professor. This might sound kind of stupid, but when in the third quiz do you need to change the milliseconds to seconds?
Third quiz. Well, I'm changing milliseconds to seconds just to be dimensionally consistent, because the answer is wanting it's looking for velocity expressed in terms of meters per second. So that was basically all I needed to know to say, well, if I need to express velocity in terms of meters per second, then that means I need to convert milliseconds to seconds just to be dimensionally consistent. So that's the only reason I did that.
Okay. So I could actually do it from the beginning and just relabel that graph instead of 10. It would
Yeah, right.
Okay.
And right, instead of 10, 20, 30, 40, it would be 0.01, 0.02, 0.03, and 0.04. That's
Okay.
correct.
Professor?
Yep.
Hey, for number 6, I think
Of 6.
Yep.
Okay, so
So the only difference in my numbers is instead of it's saying 6.3 for the original acceleration
Mhm.
function,
yeah,
it's just 6.6 for me.
and that's the only difference.
That's the only difference.
So then
And I got like 100.9, and the for A2 I got it wrong as well. I had 21.15, and they wanted me to put it as what was it, 21 flat. So I guess I'm off by like a percentage here. So I'm not really
okay,
sure.
let me take a look. So your Wally Plus says your acceleration is 6.6 minus 1.2 t. So did you get part A correct?
Yeah, well, after I finagled with the decimals, but yes.
All right. So let's just see. Let's quickly retrace. So that's your acceleration function. And part B is when, so this is your velocity function. Your velocity function is going to be 6.6 t minus 0.6 t squared, which means your position function is going to be 6.6 t squared over 2
Yep.
minus 0.6 t cubed over 3. And I should write this as x final minus x initial. So then same thing. You're right. This is going to be x final equals 3.3 t squared minus 0.2 t cubed plus, and then what was your initial x position?
3. Oh no.
That's it,
2.8.
right? Yeah,
2.8.
Right. All right. Well, that's good. That's good.
All right. Sorry.
Okay, good. That's an easy problem.
$99.7. Okay, I got 99.7 and it's still saying no. And the only thing is the 3T is 2.8T.
Okay, let me so because your initial X position is 2.8.
Yep, cyclists are moving, yes, 2.8.
All right, so this is 3.3 T squared minus 0.2 T cubed plus
2.8T.
I forgot a term here, didn't I?
Machine the was it starting velocity?
There's my squared term, there's my cubic, where's my linear term? 3T plus 3. That's interesting.
Leon's missing his 2.8 in there. It should be 2.8T. Yeah.
Yeah, that's what I did. It still gave me wrong.
Okay. Interesting. So
3.3T, 0.2T cubed plus 2.8T plus 7.3
3.3 T squared, did you say?
cubed.
Isn't it 3.3 T?
Oh, yeah, 3.3T squared minus
0.2
T cubed. Yes.
Plus
2.8
2.8
T.
2.8 T.
And then 7.3.
No, actually that's 7.3 you don't need because that's no, let's see here. I gotta backtrack 3 V final.
That's what's confusing.
Velocity function. My
Step
velocity
18.
function.
You pulled it over.
Yeah, but that might have been a mistake. Let's see. I mean, it worked out in the end, but this is my velocity function. All right, so let's just backtrack. So for you, you're saying your velocity function was 6.6 T minus 0.6 T squared.
Yep.
Plus V initial. So what was your initial velocity?
Is that 2.8
Okay, so
meters per second?
Yeah, 2.8 meters per second. So that's your version of step 10. All right, so then your X is going to be 6.6 T squared over 2 minus 0.6 T cubed over 3 plus 2.8 T plus, and then once again, what was your initial X position?
7.3.
It was, okay. So let's do this. 3.3 T squared minus 0.2 T cubed plus 2.8 T plus 7.3. Oh, and then what was your time? Yeah, at what time did you? It was
my
it was
range
zero
is
to
0
yeah.
to 6 seconds.
It was 0 to 6. Okay, so then 3.3 times 36 minus 0.2 times 6 cubed plus 2.8 times 6 plus 7.3 minus that 7.3 would be 92.4. Is that what you got?
No, I got 99.7. You minus the
Yeah, because you it's 99.7, but you're evaluating it. When you evaluate this integral here, you would literally do it like this. You would say 3.3 times 6 squared minus 0.2 times 6 cubed plus 2.8 times 6 plus 7.3. All of that minus basically this, minus 7.3. Or if I wanted to really, it would be 3.3 times 0 squared minus 0.2 times 0 cubed plus 2.8 times.
Oh, because it's
right.
I'm retarded.
Right.
All right, thank you.
Yeah.
Sorry.
I made the exact same mistake. I think maybe more than once, but yeah. Now we know.
All right.
Yeah, I
That's-
mean that was plaguing me.
Professor, how do you solve for the looking at step 18 that you have up on the screen there? How do you
Mhm.
solve when you're doing that evaluation from 0 seconds to 6 seconds?
Exactly what I did here. So I was just doing it 10 seconds ago. This is how you do it.
Okay, so you just plug in 6 and then subtract.
Yeah,
the value.
that's right, because this is the expression at 6 seconds. So correct me, let me guess. Am I guessing, did you take calculus before?
Me?
Yeah.
It's been a decade.
Okay, that's fine. And that's, yeah. I mean, the bottom line is you do have the prerequisite. So this is at t equals 6 seconds. And this is at t equals 0 seconds. So it's the whole function at 6 seconds minus the whole function at 0 seconds.
Thank you.
Yep.
Last question for me. Can you go to number 5? I missed how we got the original A.
Part A said, at what time after starting is the spot instantaneously at rest? All right, so that's, let's see, when is that spot instantaneously at rest? So, well, here's the velocity. So when this velocity equals 0, the spot is instantaneously at rest. So I need to take the first derivative of my position function.
First derivative, yep, 10.8.
Yep. So get yourself your form of this.
So yeah, mine was 10.8 minus 3 multiplied by 0.650 t squared.
0.650.
Yes.
T squared.
T squared.
So your spot came to a rest at 10.8 divided by 3 divided by 0.65 square root 2.35 seconds and some change.
2.35. I got 2.26. Oh, did some math wrong.
10 was it 10.8?
Yep, 10.8 is great.
All right, so 10.8. And again, all of this has to be set equal to 0.
Yep.
Okay.
So pull the 10.9, that's minus.
Yeah, I get 2.35339. Then you take your t value and then you plug it into your position function, which is my step 3. So for you, it's not 11.7, it's 10.8. And it's not 0.659, it's 0.650. And you use your t value, which again, you should be getting 2.35339.
Can you write that out for me? Because apparently I'm just not understanding.
How you got the 2.35?
Yeah, how you get the seconds?
Did you divide by both the 3 and the 0.65 and then take the square root?
Right. So from here, here's next step from here. I'm going to leave 10.8 all by itself on the right side. And then I'm going to bring this combination to the left side. So if I bring all of that to the left side, I'm going to get 3 times 0.65 t squared. So I go from here to there, and then t squared equals 10.8 divided by 3 times 0.65. And then you take the square root of that.
Yep. I typed it in incorrectly.
Okay.
2.353. Okay, and then I can just plug and chug from there.
All right, Professor. I'll see you on Thursday, right?
What's that?
See you on Thursday.
Oh yeah, good. Thanks. See you guys on Thursday.